Good afternoon, everyone. I'm Jinyi Yang from Steward. I'm working on high redshift quasars. So today I want to introduce you our current high redshift quasar surveys from the post-reionization to the reionization area. So my main collaborator are Steward and the figure 1 here. So firstly, this plot shows the cosmical epochs. As we know, there's an epoch we call it the reionization, and from the studies, as we know that recent studies suggest that the epoch of reionization ended at around redshift 6, and more recent studies of the quasar absorption spectrum suggested that there is a possible tail of the reionization epoch at around redshift 5.5. So we call it the post-reionization from redshift 6 to redshift 5. So our work focuses on these two epochs, the post-reionization and the reionization epoch. So quasars, as one of the non-transient, the most luminous non-transient object in the universe, will provide us more information on the early universe. So we are working on quasars and such kind of high redshift. So quasars at this redshift range are used for tools for study the early universe. The first thing we can know the evolution of the IgM state. Here there are two figures. The left one shows this is the first quasar discovered with complete computation trap at redshift 6.3. At that time, this spectrum taught us that ionization processes hadn't been completed at redshift 6.3. So this is the first spectrum in 2001 and 2001. So the right figure shows that this is the most distant quasar known at redshift 7.5. We can see this one here. This is a very obvious dumping wing of the blower of the market emission in the quasar spectrum. So quasar's dumping wing is very useful to construct the neutral hydrogen fraction at high redshift universe. We can see this. This plot shows the constraint on the neutral hydrogen fraction at redshift 7.5. We get a neutral hydrogen fraction around 0.5 to around 0.4 to 0.7. So which means at that time, at the redshift 7.5 universe is highly neutral. We haven't got a fully ionized universe at that time. And combining high redshift quasars and our high redshift Lamarck emitter and Lamarck galaxies, we can trace the ionizing history from redshift 8 to redshift 6. This is the optical depth measured of neutral hydrogen fraction measured by from the quasars and Lamarck emitter samples at high redshift. And the second one, we can know the co-evolution between the supermassive black hole and their host. And we know today we know almost most galaxy there's a black hole central of the most galaxies. And the low redshift we know the black hole mass and the M sigma relation, very famous M sigma relation. And most of the black hole mass has the black hole has a mass around 10 to 6 to 10 to 9 solar mass. And there are, in this figure, this is the M sigma relation figure. There are two 10 billion solar mass black holes discovered in local. So the question is, does such kind of object, billion solar mass black holes, exist at high redshift at early universe? And if they exist, whether they follow the M sigma relation discovered in local. So here, up to date, we know that we have discovered people working on high redshift quasars have discovered several billion solar mass black hole at high redshift. So we can many 200 quasars at redshift Helen 6 and 15 at redshift Helen 6.5. And yeah. And also two black hole with spilling black hole mass at redshift Helen 7 is 7.1 and 7.5. And among them, there are several 10 billion solar massive black holes at redshift higher than 5 and higher than 6. One at 5.3, one at 6.3. In this figure, we can show these two 10 billion solar massive black hole here. From this black hole mass luminosity plot, lumetri luminosity plot, we can see that most of the higher-redshift quasars discovered, higher-redshift quasars, following the Eisenhower equation. This line, the dashed line here, is the Eisenhower limit here. So most of the higher-redshift quasars located around this line.
Can that be a selection effect?
Actually,
it's hard to see. I mean,
yeah, actually, if they're very
those
luminous.
quasars span a very wide luminosity range, so
Yeah.
most of them are following this releasing. But there are some. I mean, there are some outliers. You can see there is a green point at a silver ending, but that quasar has a very low signal to noise spectrum. So.
At the end, maybe affected by the selection bias. They're very luminous with very high, with very massive black hole mass here at the end. They did affect that selection bias. But here, with low luminosity and low black hole mass, they're still following this line.
Right, and I guess you can still see some that fall in the middle of the.
Yeah, they're still here.
Yeah.
But the accretion, the accretion rate, the distribution of the accretion rate of high-redshift quasars has a peak around 1. Yeah. And the scatter is smaller than low-redshift. Yeah.
So tell me again, what are the contours?
Contour show low-redshift from SDSS. SDSS sample.
Do they all have uniform black hole mass measurements, or is it different methods? For
I think most of them from the mentioned 2, yeah, for initial line. As at high-redshift, the only method is the magnitude 2 line. So the question is how this billion solar massive black hole grows and how does it exist at such kind of high-redshift. So this is a plot to show the trace of the massive growth from very early universe to what we found in redshift 6. By assuming an identical accretion of the black hole from a 6 black hole to what we found. This model challenges that we need limited the 6 black hole mass at early universe. So to see the billion solar massive black hole redshift 6 and 7, we should have a 6 black hole with the black hole mass around 10 to 3 solar mass at redshift 40. So this billion solar mass black holes challenging either the black hole growth model or the 6 black hole mass. So next one is the environment of supermassive black hole. So this quasars, this slide show the simulation model. This study suggests that this red high-redshift quasars should be formed from most massive halos, and it's expected to see those highly overdense region. So we should see the overdensity around those luminous quasars at high-redshift. Well, more recent study of the high-redshift luminous quasars suggests that these luminous quasars affect the environment in a very complicated way, not only on overdensity. So maybe some studies didn't find evidence of the overdensity. So we need more sample here to study the environment. And the next one is the uranium metal observers. As we know, the quasars, they're very luminous, so their absorption spectrum provide an excellent tool to study the invariant absorption of observers. Metal observers, especially those very weak metal observers. So these two files show the result of carbon 4 and mangan 2, the invariant metal observers from those quasar spectra, from redshift 6 to redshift. So we can see that show evolution for the redshift. For example, here from redshift 6 to redshift 5 or 4, there are quick build-up of the metallicity in these observers. So from this too, it suggests that maybe there's a very quick build-up of the metallicity. As we know, the metal observer, for example, the strong magnitude observers it should be related with the galaxy. So which means that it also treats the metallicity evolution of galaxies. So that's why we are working on this redshift. We are searching for this distance luminous quasars and the post-reionization and also reionization. So I will introduce 3 quasar surveys: redshift 5, 5.5, and Helium 6.5. So we know that the quasar is hollow continuum and broad emission line, so they show a different color for most of the stars. It's a good method to select quasars. Yeah, so we're also using the color selection for our quasar surveys. See this. See the quasar template compared with the different optical and near-infrared filter curves. The quasar template, quasar emission line, landmark emission line. Yeah, from low redshift to high redshift, moving to wider reference range, and the IGM absorption lower than the electron change very quickly. So we use the different color for different redshift selection. First one is a redshift 5 luminous quasar survey. The goal is to find more missing luminous quasars, actually the missing quasars by SDSS. This function that from the SDSS, we got 300, around 400,000 quasars. Only 300 quasars at redshift 5 to 6. So it's very hard to select quasars at redshift higher than 5. The reason is we see this is an RID color diagram. It's a typical selection for redshift higher than 5 quasar selection. Here the red line shows the color track of the quasars in this plot from redshift 4.5 to redshift 6. Just go crossing this colorful contours show the locus of M draw. So just from the redshift to high redshift going across this M draw locus. So in Magorine, in 2013, they measured the redshift 5 luminous function, and it's a very great work. Their work focused on the band end, but at the bright end, there are only 8 quasars within these 2 bright beams. So to constrain the quasar function, the bright end of the luminous function, we need a larger luminous quasar sample at this redshift range. So this is our set goal of this first survey. Any more quasars, measure the luminous function, and constrain the bright end and study the evolution model of the quasar number density. So the our selection, we following the traditional RNA diagram, but to find more quasars, we relax the. See, this is the orange dash line, the green dash line show the previous selection, the first word used. The purple dash line is our new selection. We relax the RNA of color selection to cover more quasars. But we have a problem that more M-drop star combinations will be selected in our selection. So we had 2 magnified colors, the W1 and W2. See this one, W1 minus W2 can separate those quasars, those quasars from M-drops very well. These 2 blocks show the convenience of using the white color. Here show the fraction of higher redshift quasars detected by WISE following the redshift and the magnitude. So at the bright end, the magnitude is greater than 20. OS, the OS W1 and W2 is a very highly complete. It's very highly complete at the bright end. Therefore, combined SDSS optical color and the WISE infrared color, we carried out Redshift 5 luminous quasar survey within the whole SDSS footprint. So the magnitude limit of survey is around the band 19.5. So our survey from 2030 to 2050. This is the telescopes we used. Including 2 telescopes in China and also found in KT, MNT, and there's Australia and U2 chemistry major telescope. The result is we discovered around 80 new quasars, Redshift 5, with a successful rate is around 60%. So what do you mean compared to SDSS? SDSS has a successful rate around 5%. This is a survey in our large area. Yeah. So this is the result shows the redshift and magnitude distribution of our new discoveries, the red stars, compared with our known quasars, most of them from SDSS. Here, our survey significantly expand the luminous quasar sample at this redshift range. So, based on this new sample, we can get a new determination of redshift 5 lunar function. This is our new sample. We including 99 quasars at very bright end. This is magnitude from -26.8 to -29. See here, this is the plot of the redshift and magnitude distribution of our sample. Here, the first one and second and third luminous quasars are all from our survey. This is the selection function generated by using a sample of simulated quasars here to show how complete our selection is. So in the middle range, around redshift 5, our selection show very high completeness, is around 68%.
Why are you it looks like you're more complete to fainter quasars at the high redshift.
What do you mean?
It gets bright. You think it looks darker on the top. Yeah.
Oh, I think this one affected by the this one affected by the Bologne effect. Yeah. So our simulated quasar, including the Bologne effect, so with different luminosity, the equivalent with the emission line have different equivalent with, so the color will change. Yeah. So
I see. So it's moving things in color space.
Yes.
And so they go in and out of your
Yeah, they
selection
changed
box.
I think it changed to more brighter. So our I-J color cut will prevent you selecting those quasars. So this was the result of the luminous function. As our sample just focus on the bright end, so we combine our hours and the SDS strip 82 very deep quasar survey sample, and also SDS 07 sample here. Different colors show the strip 82, 07, and our quasars. The purple solid line show our final best fitting. So we found a better bright end slope and a fainter break magnitude. So use our luminous function, we can estimate the contribution of the quasars to the ionizing background at redshift 5. It's around 18% to 45%, but it depends on the clumping factor. So it still depends on the model. So using the luminous function, we can discuss the evolution of the quasar number density from low redshift to high redshift. Here, the red square here, we plot our result. We plot 3 parameters of the luminous function: the luminization, break magnitude, and the gradient slope here. This is our result compared with the result from Earth survey from redshift 2 to redshift 6. Then we can get an illusion of the luminous function. So the blue dashed line here is the RED model with luminosity illusion, density illusion model from SDS 07 quasars. Our new fitting is the red dashed line. It seems it's consistent with RED model, but we prefer a steeper slope of the luminization and a slower illusion at the break magnitude. And also, this study show maybe there's a turnover here. See, the RED model can describe the Quasar evolution from redshift 2 to 5, can describe it well, but a high redshift is not. So there seems a turnover at also the break magnitude and normalization. This is a result. It's a result from the Jiang's result, 2016 from the SDSS QLF survey, and get a more fainter break magnitude and more higher normalization. So which also should suggest this turnover here. So to answer whether there's a turnover, we need a sample just between redshift 6 and redshift 5. So this is the redshift 5.5 Quasar survey. This is the motivation of our redshift 5.5 Quasar survey. So in addition, our sample can also use for the black hole mass function study and black hole growth. I'm working on it. So here shows some preliminary plot. Here is a black hole mass measurement from local to redshift 6 and 6.5 from previous works. Our sample here is our sample located concentrated at the massive end as our Quasar, our bright, our luminous, so our black holes at the massive end. So which may have here from redshift 6 to redshift 5. It seems that there's a fast supermassive black hole growth phase. Actually, this phase has been suggested by previous studies. There's a fast supermassive black hole growth phase after redshift 6 and around redshift 4.8. So our study is also consistent with this result. So here from 6 to 5, we still need a sample for the supermassive black hole study. This is the next one, the redshift 5.5 Quasar survey. This is the first systematic Quasar survey at this redshift. Yeah, as we showed just briefly background here. These two we showed before. These two show the metal observers. As we mentioned before, you can see from redshift 6 to redshift 5, they're quickly built up. So which means that from redshift 6 to redshift 5, something changed, something happened. And this is a redshift distribution of our known quasar at high redshift, a redshift higher than 4.9 to redshift 6.5. There's an obvious gap at redshift 5.5 from redshift 5.3 to 5.7. There are only 30 quasars here. This is the reason why we got the obvious gap of the redshift distribution. 5.5 just here. This is the color chart, yeah. Here, fully overlapped with the end off. So it's very hard, it's very challenging to study quasar redshift 5.5.
Do you know roughly what type M dwarf that is?
Yeah, here, see the three different colors means already have this M4 to M6 as the type M dwarf.
Okay, so it's the yellow is M4 to M6.
Yeah, M4 to M6. So here, I also compare the Quasar template, the spectral template with M5, a typical M5 draw spectrum. And also plot SDSS, the three-band human curve. We can see that we plot these two spectrum by scaling I band to 20 magnitude, and then we will get the R band and D band magnitude. So the R band of the Quasar is the 22.1, the D band is 18.8. But for M drop, we got a very, very similar magnitude. So that's the result. It's very hard to separate those 5.5 quasars from those M drop. Only use the optical colors. So what we did is adding more near-infrared and the mid-infrared photometric data. Here, this is the plot. We still use the based on the RA color diagram. We use this diagram to limit the redshift here. The blue point is simulated 5.5 quasars, and green dotted mean this M drops. Spectroscopically identified M drop from SDSS. This colorful line previously used color section by redshift 5. This purple dotted line here, our selection to focus on the 5.5. Here, these two we used the near-infrared JHK and mid-infrared W1, W2 to separate those quasars from actual here. We firstly carried out the survey based on SDSS and URAS and VHS and OS. So just within a 5,000 square degree field, the main limit is about 20.5. This is 2015. This is a selection function of our calculus selection criteria. So yeah, it's complicated for this redshift range. And we then also carried out the survey in a larger area to get more quasars. Just actually with the development of the near-infrared surveys, this is the UKIRT Hemisphere Survey, the UHS survey. This is the yellow part. Compared with the previous URAS survey, it's mapping the J band in a 12,000 square degree field into the northern sky. So it provides a large area for our survey. And also the pan-star with big and large area optical data.
The UHS is something, it's not public yet, right?
In this August.
Okay.
Yeah. So this is our result. I just show the redshift distribution in the red part our new discoveries compared to our known quasar. And in this plot show our near-infrared detected known quasars as we use the near-infrared data. We have discovered this 31 new quasars. We doubled the 5.5 quasar sample, and we also filled the gap here. So our work this is the first uniformly selected quasar sample at redshift 5.5. We were using it to study the quasar number density evolution and also the IGF evolution and the near-zone side evolution of quasars at this epoch. These three telescopes we used come out 200-inch MMT and NU 2.3 meters. So the last one is the very high redshift quasar survey. For quasars at redshift higher than 6.5, we are searching for the most distant quasars in the reionization epoch. So then we can study the reionization history directly. There are already some surveys for those most distant quasars. As we know, the SDS redshift 6 quasars, the HTR redshift quasar, Quasar, and there are some quasar surveys based on the near-infrared surveys. We know the redshift 7 and 7.5 or from the near-infrared surveys. And some upcoming surveys based on the ERS, the super, the super HSC very deep field survey. So our survey based on, from those survey, we only got 2 quasars at redshift higher than 7 and 15 at redshift higher 6.5. So we're on the way to find more. This is a new survey, a photometric survey we used. This is the designated survey here. This is details, including details in G-band or random G-band, and the BAS and SDSS, include G-band and the G-band or random G-band, and also DS in the source data. So this is the color code we used. Here we use the data. As we know, the very high redshift quasars, they should be J-band dropout or totally optical dropout. So for redshift for all redshift higher than 6.5 quasars, we use the J-band dropout. Here's the J-minus J color, and also J-minus W1. Here is the pan-star Y minus J and the J-minus W1. This is the track of quasars. Compare with those colorful triangles and swirls and tears crossing. Show the M drop, L drop, and T drop. So our survey we are working on, we are on the way. Using MMT and Magellan and Palma 200-inch and also German engineers. This is our result up to date. up to date, we discovered this plot here only plots 16 new quasars. This plot I made it 3 weeks ago. During the past 3 weeks, we got 3 new quasars. They're 6.5, 6.8, and 6.7. Oh, this one. This is the highest redshift quasar from our survey. It's 60.99, but just the best on the landmark emission. So I think from its magnitude and the colorful redshift, it should be higher than 7. Yeah. This is a distribution, the redshift and magnitude distribution of our new sample here and our known quasar. Actually, this one, the 7.5 quasar, which was also selected by our survey, but they discovered it firstly. Here, the red stars are our new quasar. Our quasars are more luminous, averagely more luminous than first known. So our quasar sample will provide a good quasar sample for the absorption spectral study and also the near-zone side and damping wave study, since they're very luminous and we are easily to get the high signals and high resolution spectral. This is the selection function of our selection criteria. Yes, preliminary results. Since we used many different photometric surveys, we need to simulate their completeness. So, do some work here. From redshift 6.5 and to redshift 7.2 here. This is our new quasar, and this is 5 previous known quasar. So for quasar found here is the sample we used for the quasar lunar function at redshift 7. As we are providing a complete, uniformly selected high redshift quasar sample here, so it's the first time we have chance to measure the lunar function at redshift 7. Here, this is the preliminary result here. The 3 red dots with arrow above are obtaining the lunar function here compared to previous works. The different colors and the dashed lines, solid lines represent the different evolution model from redshift 6 to redshift 7. So our result is consistent with the K parameter means the decline of the quasar number density. Our result is consistent with the K parameter equal to -0.7, which means there's a very rapid decline of the quasar number density from redshift 6 to redshift 7. It's dropped quickly than from redshift 5 to redshift 6. And in addition to the lunar function, our sample can also use for the black hole mass. This is a spectral from Gemini Genius here for redshift 6.7 quasar. Yeah, we use the magnum tool to measure the black hole mass, and we get a billion solar mass black hole here. Next things we can do is the dumping wing and near-zone size. As we mentioned before, here at redshift 7, the neutral hydrogen refraction is higher than the redshift. So we can see maybe we can see some dumping wing from the quasars at redshift 6.8 to redshift 7. Actually, there are only 2 satellites of the dumping wing we have got. We have known from the redshift 7 and 7.5. Our surveys provide the redshift 7 quasar. The redshift 7 quasar show a clear dumping wing. It's the third satellite we know for the dumping wing study. Here, these 2 show the 2 examples. Yeah, so just what we can do using our quasar sample here. And this one show the neutral hydrogen refraction from the redshift. So our sample can be used to constrain the neutral hydrogen refraction evolution with the redshift. And we also use the for those dumping wing and there's also side of the neutral hydrogen refraction study, we used Gemini GMOS, RBGMOS, and also CAP-GMOS. And we also use the Gemini Genius and the CAP-GMOS for the near-infrared spectrum can provide the magnitude-based redshift measurement. And we also working on some follow-up works, data from ALMA, NOIMA, and GRE for the centimeter and the radio wavelength studies, and also Chandler for the X-ray properties of those quasars. This one is a very interesting project from our survey. Yeah. The most distant length quasar. So the original spectrum of 1D and 2D. Here we can see that this is the MRF emission and blueward nucleoside here. We can see blueward of the MRF emission. This is a redshift 6.5 quasar. You should have a very complete computer trap at this redshift range. Blueward of the MRF. Well, we do some tricks here. So this trick should be from the foreground object. If the foreground object is a galaxy, then the quasar should be lensed quasar. So here, this is the plot. This is a plot of the black hole mass and the photometric luminosity again. We saw this plot before. This object is here. Yeah. The black hole mass is also from the Jinyi's DDT time. Yeah. Still the Jinyi spectrum. We can say if this quasar is not lensed, then we will get this point here. It's very super angular accretion with the accretion rate is around 4. It's a very high accretion rate. We haven't found that at high redshift. If this one is lensed, then we will get from here, just following the angular accretion line. This one here. Then here, this show the SED of this object compared to the previous most luminous high redshift quasars. This one and the most far infrared luminous quasars, the blue one. So we can see that this one is very luminous if it's not lensed. We got an HST-DDT10. This is the HST image for this object. Then we can see it's clear. It's clear that it's lensed. We can see two components of this quasar here. This is the foreground lens galaxy here. So this is the model, the lens model. There's an Asian galaxy here. So the Asian galaxy here. Now there are 2 or 3 components of the quasars.
How does the black hole mass change because it's lensed?
Yeah, but we can get a magnification of the lens to the quasar. Then we can estimate the luminosity. Yeah.
But I was just wondering. So I thought it was a measure, like the measured black hole mass changes if you assume it's lensed versus.
Yeah.
Change the order magnitude.
Oh, it's just because the magnitude change.
Yeah.
Yeah, just because of luminosity.
Because of okay.
So as a summary, we carried on the 3 high-redshift quasar surveys at the post-reionization redshift 5, 5.5, and the reionization 8.4 redshift 6.5, and also 7 quasar survey. This just 3 results here. We discovered the quasars measure the luminal function, and the redshift 5, 5.5, we construct the first uniform size quasar sample and fill the gap. The last one is our discovery doubled the number of the known quasars at redshift higher than 6.5 and provide the excellent sample for study of the reionization history. Yeah. That's all. Thank you.
When you were talking about the difficulties with like the M stars and being able to remove those, does Gaia help you with that at all?
Actually, Gaia provides the promotion information. Yeah. Actually, but it could be helpful. But our quasar fans for Gaia to get an accurate promotion measurement. So some of them we checked our quasar sample with Gaia data adhered to database. A small fraction of known quasars have Gaia promotion data on the field, not all. Yeah. So it still helps for the high redshift.
So looking medium long term, instead of this, I'll use this color cut for this redshift, this color cut for this redshift. This is a good application of machine learning, right? So
Yes.
are you looking into developing those tools and investigating how well that works with the data you have so far?
It's a good method for the Quasar selection, but for low redshift, we didn't use that. As you know, the machine learning including more colors, including over colors. But actually, including over colors, maybe sometimes it's not better. The reason is we can see that, for example, the redshift 505 quasar, we only can separate these quasars from the M drop in only 2 or 3 colors. But machine learning, if we including over colors, then just average the factor, the difference. Then we may get we tried before, but the M drop also get it's very similar with the quasars, the result from the machine learning. But for high redshift, yes, we are working on that. And actually, there are many groups. There are also several groups working on the machine learning for redshift 7 quasars. Yeah. So you know the number density of quasars at redshift 7 drop very quickly. Yeah, only 20% of quasars at redshift 7 to 7.5 compared to quasars at redshift 6.5. So only a few. So both machine learning and color selection, the successful rate is still very low. Yeah.
The other thing is the machine learning. Most machine learning methods need a training sample, right?
Yeah.
You do not have any training sample at redshift 7.
Right.
And so
Or the models.
But you have, right?
Yeah,
I mean,
you have models,
yeah,
but
and quasar models are just, I mean, when our group discovered the quasar redshift 7.1, it's exactly the same as the SDSS average.
Yeah,
quasar, right?
sure.
Yeah.
But the thing is, I mean, the BS method meets the 7.5 quasar.
Yeah.
That's because, I mean, if you use color, you can select it, but using the machine learning, you cannot. I mean,
okay.
The 7.5 quasar recently discovered also in the UKIRT area.
Yes,
and yeah. So that's because the SED of that quasar is different from the slow sample. So yeah, that's why we.
There's a problem that the only 2 known quasar redshift higher than 7. Actually, they have very strange colors, different from what we know from the low redshift quasars. They have different colors and the different SED. So the machine learning, if they based on the simulated quasars or quasar models from low redshift, then will miss some high redshift one. Actually, it's also the problem for our color selection. Yeah.
So speaking of this, still trying to select these redshifts greater than 7. So it looked like the Y band was the most important band pass.
Yeah.
Okay, and that's just because. Okay, yeah, that's just because the Lyman alpha rate, it's just going up into Y band.
That's what it was designed for.
So if it
was to separate brown dwarfs from redshift 7 quasars.
Well, Pansars has Y too, but I guess Pansars Y is blue.
Yeah.
So if they could do another
newer than you kids.
If they could do another UHS survey, you would want Y band, although a bunch of other people probably want K band instead.
Yeah.
But
Currently, we are doing the first photometric on Pan-star Y band in the UHS area because you do not have Y band from UHS. So.
Right.
The Y band, the Pan-star Y band has some, maybe it's a problem. It's the efficiency of the Y band is not homogeneous during the whole survey. So sometimes they cannot detect it. Sometimes yeah. So that's why we did a full supplementary from the image, not the catwalk.
more questions? All right, let's thank Jinyi again.